In this video, I'm going to solve diffusion equation, and the numerical method that I will use is finite difference method. Since this course is all about finite volume method, but to make a comparison with finite difference method, we will see how finite difference method uh, how it works on diffusion equation or any other equation. So I already have written the diffusion equation. Probably you remember that there is a parallel heat equation also look like this. For example, we have partial T by partial T alpha partial square T by partial x square. This is heat equation. This is also called diffusion equation, but sometimes people call it diffusion equation when this U represent concentration of some contaminant. And here in this case, the equation is called heat equation, or T is the temperature. So I'm going to solve this diffusion equation. Here D is the diffusion coefficient. The first process of applying finite difference method is to generate a grid, which I already have drawn the nodes. These are the nodes. These nodes can be constructed from the formula which is written over here, delta x b minus a over n. Remember that in finite difference method, this n is called subinterval. Subintervals. Some people mistakenly call this n as number of grid points, which is not correct. Actually, this idea of finding the width between 2 points is coming from calculus 1 when we study Riemann sum, calculus 1. And there we discuss actually what is n. N is at subintervals in that case. Okay, so for simplicity, I have drawn 5 nodes. There are 5 nodes. You can count it 1, 2, 3, 4, 5. And the number of subintervals are 4. 1, 2, 3, and 4. There are 4 subintervals. It means that I can put n is equal to 4. In this problem, my aim is to solve this diffusion equation on the domain 0 to L. Since I'm not going to solve this problem particularly for some particular domain, 0 to 1 or 0 to 2, something like that. The example I have given over here is for your own understanding about the width of the mesh. Okay, so we will keep this n as it is written before. Now, since we are going to apply the finite difference method, we can also write the equation for the node points, and this is written like this: I delta x. If the domain is from A to B, then we should start this xi from A and write like this: I delta x. If the domain is from 0 to B or 0 to L, something like that, then this A will become 0 plus I delta x. Then you can create your mesh like this. For example, I0 mean x0, I1 mean delta x, so on. And xn minus 1 is equal to n minus 1 delta x. So these are the node points. Let me just solve this diffusion equation over here. And I write the equation again: partial u by partial t is equal to alpha, not alpha, but d, partial square u by partial x square. In this equation, there are two kinds of derivative. One is the time derivative, and another one is the space derivative. And there are two space derivatives over here. For space derivatives from finite difference method, we know that we can apply center difference formula. U n I plus 1 minus 2u n I plus u n I minus 1 divided by delta x square. Remember that the notation u n I means solution at nth level, and at x is equal to xi. When we have u of x, it means that the solution is continuous since x is continuous. When we have xi, it means that the solution, the domain is discontinuous, domain is discrete, not discontinuous, domain is discrete. So the solution u is also discrete, and we write it like this. And for time interval, we use n. N means you are using the time solution at time interval n at nth level. Okay, since u is a function of x and t. On the left hand side, we have time derivative. For time derivative, we use Euler's method, RK methods, RK2 and RK4 methods. And for for Euler's method, we can apply un plus 1 Euler's method over here over delta t. Although this is forward method in time, but it is explicit Euler's method. We just solve it, keep the unknown on the left hand side, un plus 1 I, un I plus d delta t by delta x square, un I plus 1 to un I plus un I minus 1. So this is the equation which will give you a solution, finite difference method solution. As I said earlier, we are not going to solve this problem. I'm just going to give you a different perspective of finite difference method and finite volume method. This parameter is actually called R, which is von Neumann number, d delta t by delta x square. This is called von Neumann number. So this is the discretization scheme for diffusion problem. In the next video, I will not solve, but give you a glimpse of applying finite volume method on diffusion problem. Thank you for watching.